Moving on, so far we have seen how over here that a density altitude is based on atmospheric density surrounding you, ambient air density which is surrounding you. Otherwise, uh, in case of altitudes of true altitude, pressure altitude, flight level, we have all altitudes based on pressure. In case of density altitude, we have altitude based on density. In case of density altitude being high, means air density is very low in that air mass. As a result of that, when we have less density, that means thin air, that means bad for aircraft performance. Density high means high air density, low density altitude, thick air, good for aircraft performance. Okay. Then we saw three scenarios in which we started with ISA pressure level or ISA atmosphere, ISA conditions. Then we moved to warmer than ISA temperature conditions. We had a combination of three elements: temperature hotter than ISA, pressure lower than ISA, and humid air. This combination is very unsafe or bad for aircraft performance. Your takeoff roll will increase, your landing roll will increase, and rate of climb will decrease. So over here, when you are warmer than ISA conditions, this combination will produce a density of air which is much less than ISA. As a result, you will get high density altitude. Now, what is high density altitude? That means what? The altitude at which you will find the ambient air density. So, in this case, you are technically at mean sea level, but you have density which is existing at 20,000 feet. So, at mean sea level, you are getting air density which is supposed to be at 20,000 feet. So, although you are at mean sea level, the density altitude will be 20,000 feet. Aircraft will behave in a manner which it will behave were it if it were at 20,000 feet. So that's why your aircraft performance will get impacted. In third condition or in third scenario, your density altitude is low. Okay, low density altitude means aircraft performance much better. Okay, so as I told you as I told you that rate of climb decreases as your density altitude increases. Okay, or as your altitude, just in case altitude increases, let's say your airport is located at higher elevation, like mountains, okay, like that, mountains, hills. So over there, when you are at high altitude, the density of air that you will find there will be much lower than the density of air at mean sea level. And as a result, you will require much more takeoff distance, rate of climb will increase. That's why. So here you can see that increased time, fuel, distance by 10% for each 10 degrees Celsius above standard temperature. Now this table in front of you, this information is being taken from Cessna 152, okay, a POH, Pilot's Operating Handbook. As I told you, all pressure instruments and aircraft are designed in such a manner that they give maximum best performance at sea level conditions, ISA atmospheric conditions. So all the performance calculations given by the manufacturer are based on standard conditions, and that is always mentioned on that performance graph or the table. Okay. And if there is any deviation from that, you have to either add a particular value or subtract a particular value from the numbers given here. Now here you can see as altitude increases from sea level to 1000, 2000, so on and so forth. When altitude increases, the atmospheric pressure decreases with altitude, and as a result, air density also decreases, because as atmospheric pressure decreases, the air will expand in volume, and when volume expands, density decreases. So with that, rate of climb also decreases. As you can see, 715 at sea level has become 505 at a level of 5000 feet. Okay, so rate of climb decreases. Next, takeoff distance. Here you can see temperature columns given 0, 10, 20, 30, 40. Now when the temperature at mean sea level is 0 degrees Celsius, the ground roll or the ground run there is 640 feet. When temperature increases to a temperature of 10 degrees Celsius, the ground roll or ground run, that is, the distance aircraft starts from a stop to the point of its liftoff. The total distance from the start of the takeoff roll to the point of its liftoff is your ground run or ground roll. So as temperature has increased or become warmer than 0 degree, the ground roll required also becomes higher. 605 has 640 has become 695, 695, right? So what happens as temperature gets warmer and warmer, air density goes on decreasing. Decreasing air density means thinner and thinner air in entering your aircraft engines, and therefore the power generated is less and less. Same goes with 20 degrees Celsius 755, after that 30 degrees Celsius 810, and 40 degrees Celsius 875. So this is how the ground run goes on decreasing. This may be a printing error. Next, rate of climb data. Same as altitude increases, you can see the rate of climb also decreases with it. 765 has become 670 at 2000 feet, 570 at 4000 feet, so on and so forth. Now just let's focus at sea level conditions. When your airport is at sea level, as your temperature increases from 0 Fahrenheit to 20, 20 to 40, what has happened to your rate of climb? 765 has become 700, which has become 630. So as temperature increases, rate of climb decreases because of less and less air density. Now, when we took that example previously of three conditions, one where airport is at ISA atmospheric conditions, airport is surrounded by warmer than ISA atmospheric conditions, and the third example which was colder than ISA. In all these three conditions, we looked at three elements of atmosphere: pressure, temperature, and humidity. Right? Now, this pressure, temperature, and humidity, a combination of these three important elements, will determine your density altitude. If it's going to be high, very high density altitude, low or very low density altitude. Okay, so you have to remember density altitude is controlled by three factors: pressure, temperature, and humidity. Pressure, temperature, and humidity. Now let's inspect every element one by one. Here you have two containers in which there are air molecules trapped. One has 2.992 inches mercury pressure. Let's call it low pressure. Another container has a pressure of 30.92 inches mercury. That becomes your high pressure. Okay. You can clearly see that in a low pressure cylinder, due to low pressure, the molecules are away from each other. But in a high pressure cylinder, the molecules are closely packed or very close together. Right? So high pressure, the conclusion that we draw is high pressure will compress the air and therefore density increases. Low pressure will expand the air and when air expands, density decreases. Density decreases. So this is one. Second, about temperature. Now when you consider temperature, what happens? Here you have cold temperatures, here you have warm temperatures or hot air. In cold air, the molecules are close together compared to molecules in hot column of air or hot parcel of air. So what is the conclusion here? Cold temperatures will give you high air density, will give you high air density. But hot temperatures will give you low air density. Low air density. Remember this. Third, humidity. Now here you have 0% humidity or dry air. Now when air is dry, you have mass of 440. When air is humid like here, full humid 100% to capacity, mass becomes 420. So mass has decreased from 440 to a mass of 420. And now density is inversely proportional, correction is inversely proportional to volume and directly proportional to mass. So when mass decreases, your air density will also decrease. So with humidity in air, your air density will decrease. Remember that. Air being dry, density will increase. Next, yeah, the result of all these three factors, pressure, temperature, and humidity, is that your aircraft performance will be influenced. When you have favorable combination of pressure, temperature, and humidity, you have performance which is good, better. But when the combination is bad, when you have hotter temperatures, lower pressures, very humid air, the performance given by your aircraft will be poor. Basically, the performance will be at risk. So here you can see clearly that at 0 degrees Celsius, the ground roll required for takeoff is 1425. Over here, the same ground roll required at 35 Celsius is 1854. So as temperatures increase, density decreases. Density of air becomes thinner and thinner, and as a result, you need a much larger amount of takeoff roll. Okay, so that you compensate for the decrease in air density, extra amount of air enters the engine and you have sufficient engine power to lift off. Next, same altitude, temperature, humidity. These three factors are the controlling factors for your aircraft performance. These three can make or break your aircraft performance. Okay. So favorable combination of altitude, pressure, temperature, good for performance. Bad combination meaning hotter temperatures, lower pressures, and humid air. Not good. Next point, high density altitude and low density altitude. So what will give you high density altitude? What conditions? Temperature going up, temperatures getting hotter and hotter, and pressure going down. Lower and lower atmospheric pressure means high density altitude. Temperatures going down, but pressure going up, low density altitude. Low density altitude means the density altitude is getting closer and closer to the elevation of your airport where you are situated. High density altitude means, like we saw in the previous slide, you may be at 0 feet mean sea level, but if the density altitude is 20,000 feet, actually you cannot take off from that airport. The solution or the course of action that the pilot will have to follow for that aircraft will be to wait until temperature cools down, until pressure rises, until humidity in air decreases and density altitude decreases to a very low amount. Okay. Next, cold dry day at sea level. Here you can see on a cold dry day, the aircraft is able to take off from this point or lift off from here. But on a hot humid day, and that too at 5000 feet elevation where pressure will be much lower than the pressure at sea level, this combination is a deadly combination. Okay, and that on that particular day, that particular airport, the aircraft is not able to take off only. Okay, the amount of runway length available to that aircraft was insufficient, and therefore the aircraft overruns the runway, overshoots it, and gets out of the runway. In such cases, such scenarios, if there is a stopway beyond the runway end or beyond the end of the runway, the aircraft will stop or will come to a stop in that stopway in that area. But unfortunately, if unfortunately there is no stopway and there is just mountains, city, people living beyond the runway end or beyond the airport premises, that aircraft will overrun the runway. Maybe at that particular speed, it might overrun the airport premises and go beyond. the airport premises. So that's a very bad aircraft accident. And in YouTube there are so many videos in which you will get to see such videos in which, due to bad flight planning, or if pilots have taken the concept of density altitude too lightly and not calculated it before taking off, before flying that plane, that they have overshot the runway, overran the runway, and faced with an accident. So before every flight, cross country flight, airlines, you have to do it. But during flight training, some people do their cross country flight planning, calculate density, altitude, check that all parameters are within safe limits, and then take off. But some people also opt for shortcuts, and they overlook or they skip all these important calculations and just fly. So that is very unsafe habit. Next, high density altitude effects on flight. Another example: density altitude is sea level. Takeoff roll 1300. Density altitude at 5000. Takeoff roll increase to 1800. Density altitude sea level, rate of flying 1300. At 5000 feet, density altitude is 1000 feet per minute. So it has decreased. ISA. In ISA, relation between altitude, temperature, pressure are fixed. Okay, we have fixed lapse rate. Everything happens according to that set rules, set theories. But in actual atmospheric conditions, seldom do we get atmospheric conditions or lapse rates which are equal to ISA lapse rates or ISA values. Sometimes we may have lapse rates which are much more than ISA lapse rates, temperatures hotter than ISA, temperatures colder than that, etc. As altitude increases in ISA, air pressure and temperature decreases. Decreasing pressure tends to expand air, thereby decreasing its density. Decreasing temperature tends to compress air, thereby increasing the density. The effect of pressure change is the dominant factor. So as altitude increases, the pressure, temperature and density all decrease at a fixed rate. At a fixed rate. So over here I will like to write this. There are two conditions that you have to look at: ISA conditions and non-ISA conditions. Now in ISA conditions, as altitude increases, as altitude increases, what happens to your atmospheric pressure? Pressure decreases. When pressure decreases, what happens to your what happens to your density? Density decreases. As altitude increases, your temperature decreases. Now what we have learned from so far, if we go by that, when temperature decreases, your density should increase, right? But what do we observe in the atmosphere, ISA atmosphere, let's say, that as altitude increases, density decreases. That is what is the rule. Density, the final output that we get to see is that density decreases. So here we have density decrease due to pressure decrease. Here we have density increase due to temperature decrease. So out of these two, why density decreases, why not it increases? That's because the pressure is the dominant factor. Out of pressure and temperature, the pressure is the dominant factor. Pressure is the dominant factor, and that's why your with increase in altitude, atmospheric pressure will decrease. With increase in altitude, atmospheric pressure will decrease, not increase because temperature also increases. Now let's take the example of non-ISA conditions. In non-ISA atmospheric conditions, same thing. With increase in altitude, pressure decreases, that's for sure. Your temperature will also decrease. But in such conditions, non-ISA conditions, the real atmosphere that we live in, okay, in that case, the lapse rates will differ from the standard lapse rates. Sometimes we have very slow, shallow lapse rates when the atmosphere is stable. When atmosphere is unstable, we have steep lapse rates, so on and so forth. So this lapse rate, in this case, the density, atmospheric density will be determined, atmospheric density will be determined by the dominant lapse rate, by the dominant lapse rate, right? If the lapse rate of pressure is more than temperature, pressure will be the dominant factor. If lapse rate of temperature is more than pressure, then temperature will be the dominant factor. But in ISA, we know with certainty for sure that pressure is the dominant factor. Effect of the pressure change is the dominant factor in ISA. In real atmosphere, rates of change of pressure and temperature with changes in altitude are not fixed. Are not fixed is the important point. Okay, like ISA, unlike ISA, in case of real atmosphere or non-ISA atmosphere, the rate of change of density with altitude is not fixed. Lapse rate will determine that. It is therefore possible that pressure and density at any given altitude do not conform to ISA values. It is possible that pressure and density at any altitude will not conform to the ISA. So what is density altitude? It is atmospheric density expressed in terms of altitude. This altitude will be found in ISA, okay, which corresponds with that density in the standard atmosphere. So let's say at mean sea level, previously we saw that the density was 50% of sea density at sea level, and that 50% of density is found at what level in ISA? It is found at 20,000 feet. So that is the meaning of this definition. Atmospheric density expressed in terms of altitude, which corresponds with that density, that altitude should correspond to that density. So if 50% of density, 50% of mean sea level density, okay, will be found at 20,000 feet. So that's the relation between them. Half 50% or half of mean sea level density equals to 20,000 feet. So atmospheric density, which corresponds with that density in the standard atmosphere, in the standard atmosphere. Next very important question often asked in your check rides, SPL Viva exam, airline interviews. Why do we calculate density altitude? What is the significance of that? So like I have so many times repeated now, density altitude is used for computing and predicting. At the time of takeoff, when we take off from our airport, okay, when we start planning for our flight, we have actual numbers with us, actual atmospheric numbers with us, the temperatures, pressure values, the condition of the atmosphere, the weather, that are current updated. But when we do the same planning, sitting in one place, we do planning for takeoff and landing as well. If we are going to land 2 hours hence or after 2 hours, we also have numbers for the landing destination airport. But those numbers won't be accurate because those will be forecast temperatures, forecast pressure values, forecast weather. Okay, so that is forecast or that is what is expected, but that is not the reality. So that's why density altitude is used for computing and predicting. Okay, we can compute the density altitude for our takeoff airport and we can predict the density altitude for a destination airport. After 2 hours, that density altitude can even rise further or maybe it can decrease. We don't know. Okay, so we can only predict based on predictions or forecast reports. Aircraft performance, engine performance. Aircraft performance means lift, landing roll, takeoff roll, rate of climb. Engine performance means how much thrust or power it is generating, including takeoff, climb, landing instead of through or pressure altitude. Instead of through or pressure altitude. Two definitions of density altitude. Density altitude is pressure altitude at which prevailing density occurs in ISA, or it can also be called elevation at which prevailing density occurs in ISA. Now pressure altitude can be equal to elevation when airport is at mean sea level. In that case, elevation and pressure altitude will be equal and therefore these two definitions can go hand in hand. Density altitude equals to ambient density minus ISA density divided by density lapse rate. The second formula, which is again more important than that previous formula, is that because you will get numerical sums in which you will have to find solutions using this formula. So here pressure altitude plus 118 into ISA deviation, meaning there is a relationship between density altitude and pressure altitude, right? You can obtain density altitude from pressure altitude only, and the relationship between them is 118 into ISA deviation. Okay, so density altitude can be more than pressure altitude, okay, by 100 and by the value of 118 main value, or it can be less than pressure altitude by value of 118. So you have to remember that that can be an important question for DGCA. Second thing, in some books they have given 118, some other books they have given 120 instead of 118. Okay, so no issue. Check the option or select the option which is closest to your solution that you find. So let's solve this question. Find density altitude. So density altitude is pressure altitude plus 118 into ISA deviation. So what values do we have? We have pressure altitude, but we don't have ISA deviation directly supplied to us. We have ambient temperature given. From that we can find ISA deviation. Now what should be the ISA temperature at 0 foot or mean sea level? It should be how much? At mean sea level it should be 15, but actual temperature is given to be 10 degrees Celsius. So what is ISA deviation? Actual minus ambient. So ISA deviation is 10 minus 15. So which is minus 5 degrees Celsius. Let's substitute the values. 0 plus 118 into minus 5. So plus into minus minus. 118 into minus 5 is 590 or minus 600 feet. So density altitude is minus 600 feet. This means what? If I have to draw a diagram, here is your airport. At 0 feet or mean sea level, right? So your aircraft is at mean sea level. Now let's find out the performance your aircraft will produce. Will it produce a performance that you should get at mean sea level? Will it produce a performance? Will it produce a performance which you are supposed to get at any altitude above mean sea level, or will it produce a performance which you are supposed to get at when you go below mean sea level? So in this case, your density altitude is minus 600. That means you are well below the mean sea level at minus 600 feet. Well below the mean sea level at minus 600 feet. That means the performance that will be produced by your aircraft will be much more than the performance it will have produced at mean sea level. At mean sea level, more than that. If the density altitude would have been plus instead of minus 600, so that means your aircraft would have produced a performance less than the performance it would have generated at mean sea level. Okay, so this is the whole concept. Next thing, again I have told you, I will repeat this note. Pay attention to questions in exam, whether it states standard atmosphere or non-standard atmosphere. Standard atmosphere pressure is the dominating factor. Non-standard atmosphere pressure or temperature can be, both get chances depending on lapse rates. So over here, if pressure increases while temperature increases in ISA, so if pressure increases, density should also increase. If temperature increases, density should decrease. So what should be the final output in its ISA conditions? So the final consequence should be a increase in density due to pressure increase. In ISA, pressure is the dominating factor. Question 2 states pressure increases and temperature also increases in a non-standard atmosphere. Now, in a non-standard atmosphere, we cannot say or predict with certainty that pressure will be a dominating factor. Temperature can also be, depending on the lab state. So, you will select that option which will have this word lab state. Depending on lab state, both pressure and temperature have equal chances to control the density. Okay, so this is another important thing. With this, we come to the end of this lecture. So far, I have divided this lecture into two parts: density altitude 1 and density altitude 2. Watch both these parts multiple times, make notes, understand this. Okay, a quick recap: we have seen what density altitude is, how density altitude is different from other altitudes that we use from altimeter directly. What is the meaning of density? Okay, that is how closely packed or loosely packed a substance is. Then we compared three scenarios: ISA, warmer ISA, colder ISA, and we saw how aircraft performance will vary from one to another. Right. After that, we saw the three controlling factors of density: pressure, temperature, humidity, and had a close look at each one of them. After that, we saw how performance, with the help of diagrams and pictures, how takeoff roll increases with high density altitude, how rate of climb decreases with increase in density altitude. Further, we saw how in ISA atmosphere, the relationship between pressure, density, altitude, temperature are fixed. But in non-ISA, this keeps on varying depending on lab state. Okay. Further, we looked at the two formulae, and most important, why density altitude is important, and the definition of density altitude. With this, we have come to a very good end of this lecture. I hope this lecture was productive for you all. You learned something new today. Definitely hit the like button if you have liked this lecture. Subscribe to this channel, get timely updates, and share this video with everyone. Thank you for your time. All the best. Keep learning.